you got a couple of people who take 5 tests, okay? And don't write this down because this is all intro. So just watch and enjoy. It is the thingy on. Thank you, Fatima. Hello, the audience at home. So you've got 3 kids who take 5 exams, right? The first kid, he takes 5 exams and he gets an 82, an 82, an 82, an 82, and an 82. You guys okay with that? We've got another kid, he takes 5 exams. He gets a 15%, he gets a 21%, he gets a 26%, he gets a 28%, and he gets an 82. And then the last guy, he gets a 70, let me think, what do I want him to do?
97.
Yeah, let's say he gets a 97, a 98, a 96, a 94, and an 82. Okay? Is it obvious to you who's got the higher grade in the class?
Number 2.
Yeah. Okay, great. So now let me give you 3 graphs. Okay? And these 3 graphs are going to be a little bit different from that. And frankly, I messed up the tests. I should have. Oh, poo. Can I change this? And it doesn't matter, even it's being videotaped. I actually messed this up. Let's say these are 3 basketball players. Okay. Let's go with that. So everything I've said thus far is just a complete waste, but that's okay. I got 3 basketball players, okay? And this first player plays in 5 games, and he scores 0 points in the first game, 5 points in the second, 10 points in the third, 15 points in the fourth, and 20 points in the 5th game, okay? You guys tell me, by the way, what's his average? What's his points per game average?
10.
Those of you saying 10 are correct, right? And you don't even have to add the 5 scores and divide by 5. You just know you got 10, take 5 away from here and put it to there, that's 10. Take 10 away from here, put it to there, that's 10. He's obviously averaging 10 per game. The next guy, he scored 0 points, and then 2 points, and then 3 points, and then 5 points, and then 20 points. Tell me, his first game was 0 and his last game was 20. Is his average points per game going to be 10? Yeah, no way. It's going to be higher or lower?
Lower.
Yeah, lower than 10. And how about I've got another guy, he scores 0 points, then he scores 10 points, then he scores 15 points, 18 points, then 20 points. Tell me, is this guy's average per game going to be higher or lower than 10?
Higher.
Oh, good for you guys. You guys get that. Well, we can do the same thing with the graph of a function. What if I had a function whose graph looked like this? Okay? And this here, let's say this is 20, alrighty, and this is 5. I can talk about there being an average value to this function, correct? That is, if you think of this function as not just 5 games, but maybe an infinite number of games, where each game resulted in a point value, right? On this game, I scored this many points. On this game, I scored that many points. On that game, I scored that many points, okay? But if I were to get the average of all of these games, what would you suppose the average would be?
For which one?
For this guy, for this straight line, where he started at 0, he ended with 20, and he had an infinite number of games whose point values followed this straight line.
4.
Wait, that's 20. Average points per game.
Oh, 10.
10, right? You'd expect it to be 10, okay?
I was thinking slope.
And so, oh, okay, yeah, the slope is 4. But the average value of this function is 10. That is, if you added up all those point values and divided by the number of games, you'd get 10. Now, it just so happens you've got an infinite number of games here, but you've also got an infinite number of points, but you add them all up, divided by the number of games, you get 10. So let me give you another graph. Here's 20, here's 5. Suppose this graph looks like this. Okay? Tell me, would you expect the average value of this function to be 10 as well, or is it something else? What do you think the average value of this function is? More than 10, less than 10, or exactly 10?
Less than 10.
How many people are thinking the average value of this function is less than 10? Okay, good. You guys get it, right? Because he played all these games, and most of these games he got really low point values. until over here. I mean, here's 10, right? You know, he doesn't start hitting 10 until, you know, his 4.5 game. You know, most of his games he's scoring below 10. So you'd expect the average value of that function to be less than 10. And similarly, here's 5 and here's 20. Okay. How about this graph? Would you expect the average value of this function to be less than 10 or more than 10? More than 10. Okay. Well, we're going to learn something about getting the average value of a function. And again, I'm not going to try to weasel it out of you. I'm just going to tell you. It turns out we get the average value of a function by getting the area under the graph and then dividing by the x distance, the width of the graph. That's how I'm going to end up getting the average value of the function. So the average value of f of x in this case is going to be the area of this triangle, which is 1/2 times 5 times 20, and then it'll be divided by 5. So the average value of this function is going to be 10. Whereas the average value of this function, if this is f of x, the average value of this function is going to be the integral from 0 to 5 of f of x dx divided by the width of your interval. And that's going to be true for this function and that function. And can you see visually that this function here, because it's got a lot more area, which is a measure of how many points he scored, because this function has a lot more area than this function is going to have a much higher average value. Well, that's what we're doing today. We're finding the average value of a function. And the way we do it is to get the area between the function and the x-axis, then divide by the width of the region. So let me go ahead and start on this. Let me see. Okay. Here comes my justification for why the average value of a function equals the integral from a to b of that function divided by b minus a. That is the area between the function and the x-axis divided by the width of the region itself. Here's my justification for it. And now again, I'd say you don't even have to take notes. You can just watch and enjoy. Okay? You play basketball. Okay? In the 5th through 11th games, here's what you score. You score 10 points, 12 points, 8 points, 10 points, 15 points, 20 points, and 14 points. That's what you score in those 7 games, your 5th through 11th games. You guys okay with that so far? Okay. And it's easy to get the average, right? The average, you just add up the points and divide by the number of games. So in this case, the average is going to be 22, 30, 40, 55, 75, 89. 89 points over 7 games. And that ends up being 1, 19, 2, 14, 5, 7, about 12.7 points per game. But I can represent this graphically. Here's your 5th game, 6, 7, 8, 9, 10, 11, 12. What is this top game, 20? Okay. I can say in his 5th game he scored 10 points, 6th game he scored 12 points, 7th game he scored 8 points, 8th game he scored 10 points. Wow. 9th game he scored 15 points, 10th game he scored 20 points, and the 11th game he scored 14 points. Okay? I just made a graph of the points. This is points, and this is games. All right? And you can think of this as a graph, as a continuous graph, if you like. But what I ended up doing was adding up rectangles. I said, okay, this first rectangle is 10, the next rectangle is 12, the next rectangle is 8, then this rectangle is 10, and so on. And then finally that rectangle gets me to there. I'm getting the area under that dotted line. By the way, to get the area under the dotted graph, what am I using? LRAM, RRAM, or MRAM here? LRAM. Hope you see I'm using LRAM, right? I'm doing LRAM. So what I actually did in calculating this average is I estimated the area under the graph, right? I used LRAM to get the integral from 5 to 12 of f of x, where f of x is my, my function of how many points I'm scoring per game, and then I divided by 12 minus 7. And then finally, I just want you to see, so are you okay with that? That whenever you get the average of a bunch of numbers, what you're actually doing is LRAM to get the area under a curve and dividing by the, 12 minus 5. My bad. Wow, not even close. I was like the Lakers last night. Anyone watch the Lakers last night? No one watched the Lakers last night. You did? I was fast forwarding by the end of the first half. I'm just fast forwarding through, right? Because I'm just going to watch them lose. And then suddenly they caught up and they were ahead, and then they lost. But I mean, they were down by 22 points. Honestly, I was just fast forwarding through the game, and then Jordan Clarkson brings them back. But they don't have enough Jordan Clarksons on that team, so there you go. Okay. So I want you to see that whenever you get the average of value of a bunch of numbers, all you're actually doing is estimating the area under a curve and then dividing by the interval that the curve is graphed under. That's what you do every time you get the average of a bunch of numbers. And so what happens if instead of 7 games, what happened if you played 700 games, right? Or 7,000 games, or 7 billion games? Well, I want you to see that you can still get the average value by adding up a bunch of rectangles and dividing by the width of the region. And so that's what we do. That's how you get the average value of a function, is you just get the area between the function and the x-axis and divide by the interval. And so now here comes the first thing you really have to write down on this lesson. I'm hoping I convinced you of the veracity of doing this to get the average value of a function. Because now the rest of this class is just you mindlessly plugging in. So here we go. Average value of f of x on the closed interval from, just 1 second, where is it? Where do I have that? I've got my definition somewhere. Oh, there it is. On the closed interval from A to B is written as follows. The way our textbook does it is they do AV of f equals 1 over b minus a times the integral from a to b of f of x dx. That's it. And this is one of those things where, you know, learn it, live it, love it sort of thing. You cannot forget this. Every AP exam, they'll ask you at least one, usually 2 or more questions where you have to have this knowledge. And I'm just hoping that my big, long intro will make this stick in your head, that it's the area between the graph and the x-axis divided by the width of the region. You know, that's the average value of a function. So hey, let's do one, okay? Get average value of y equals x squared from 0 to 2. That's the question I'm going to ask you. Before I have you haul off and punchy on your calculator, I just want to ask you this question. Here's the graph of y equals x squared. All right, and I kind of missed it, but oh well, whatever. Tell me, if this were a straight line, if my function was a straight line, straight from 0 to 4, if that was my function, what would the average value of that function be? 2. Good for you. The average value would be 2, right? But I don't have this green function. My function is the parabola. Tell me, would you expect the average value of this function to be bigger than or less than 2? Hope you guys are getting less than. Please do this problem now. Just mindlessly plug into your calculator. Good luck. I'll give you a... When you do, is anyone having difficulty getting integrals on their calculator? Like, does anyone not know how to do it still? Because I need you to do this. Let me see your crazy calculator. Okay, I'll go ahead and press math. And then 9. Oh, okay, put a 0 there and a 2 up top. And then put x squared. And then another x. Yay. You're welcome. Anybody having difficulty getting integrals on their calculator? Daniel? I don't know. I may not be able to help you with that, but these Casios just defy logic.
I'm kind of there, but
what the heck? Oh, but it says graph it. You know, you're gonna have to come after school, Daniel. These Casios, like I said, they're just impenetrable to logic. You know, it'd be like opening a door where the way you open a door is to like turn 5 different handles or something. It's freaky. Casio. They're cheaper than TIs. That's good. They're completely unusable. That's bad. Okay, you guys get that this was 2 2/2, that is 8 thirds? So this ends up being 8/6, which is 4 thirds, which is 1.33. Anybody get 1.33? Good, so we got the result we expected. The average value is below 2, it's 1.33. Okay, by the way, what if I asked you to get the average value, instead of the average value of y equals x squared, what if I asked you to get the average value of y equals rad x? Right? The average value of y equals rad x, where 1, 1, and then 2 comma rad 2. Well, oh, that's kind of dumb. I forget that one. Don't worry about it. Let's just go on.
How about negative x squared?
Yeah. Okay, it is now time for us to learn the mean value theorem for integrals. The mean value theorem for integrals. Mean value theorem for integrals. I want to remind you what the mean value theorem says conceptually. Okay, here's what the mean value theorem says. It says that the average value, or the average rate of change from A to B, the average rate of change of a function from A to B is going to be equal to the instantaneous rate of change of the function somewhere between A and B. The average rate of change of f of x between A and B equals the instantaneous rate of change somewhere between A and B. Maybe I should say, instead of between A and B, can I just say from A to B? Let's do that. Yeah, my bad. The average rate of change of f of x from A to B equals the instantaneous rate of change somewhere between A and B. That is, it says this. If I've got some function, let's say, that goes like this, where here's A and here's B, where the slope of this line is the average rate of change from A to B. That is, if this is a trip to Las Vegas, and this is distance in miles over time in hours, alrighty, then the distance you travel divided by the number of hours it takes to travel it is your average speed as you drive to Vegas. Well, the mean value theorem says sometime during this trip, your instantaneous rate of change, which is the slope of the tangent, has to be equal to your average rate of change. The mean value theorem says if you took 4 hours to drive 240 miles to Vegas so that your average speed for your whole trip is 60 miles an hour, then somewhere on your trip you had to actually be going 60 miles an hour. The average rate of change from A to B equals the instantaneous rate of change somewhere between A and B, and we call that special point C, you know? That's the mean value theorem. Well, now we get a mean value theorem for integrals. And let me tell you about that right now. If I've got the average value of a function, like in this case, the average value was 1.33, then somewhere from 0 to 2, the y-coordinate has to actually be 1.33. Okay? Somewhere along the line, your functional value has to be equal to the average value of the function. And that's what the mean value theorem for integrals says. Okay? If f is continuous on the closed interval from A to B, then at some point C in the closed interval from A to B, f of C equals the average value of the function. second. Larry Shana's room. Good, how are you doing?
Yeah, I'm in trouble.
Oh, okay, yeah, where's this happening? C4? Yeah, I'll be there at the beginning of SSR. No, nah, they're good kids. It's AP physics. They'll just sit there reading and eating. No coverage required. I mean, I'm going to have to be back before the end of SSR. Okay, great. All right, thanks a lot. Bye-bye. Okay. Here. So does that make sense? That if I've got an average value of a function, then somewhere that function has to have that value. Okay? It'd be like if I don't know, just kind of the same thing as that. So, but here's one thing I want you to show you about the mean value theorem for integrals. Look at this. Do you see I can multiply both sides of this equation by b minus a? So I get f of c times b minus a equals the integral from a to b f of x dx. So I want you to see that there's an additional graphical meaning for this average value of a function thing. It's telling me that the area under a graph is equal to the average value of the graph multiplied by the width of the region. That is, look at this guy here. Remember how the average value of my function was 1.33? The average value of this function was 1.33. What that's saying is the area of this rectangle, where the height is the average value of the function, and the width is the interval from 1 to 2, the 0 to 2, I mean the width is 2 in this case, is equal to this area. This black area is equal to the green area, and that's what defines the average value of a function. So suppose I gave you this graph. Let's go from 1 to 4. And suppose my graph looked like this. Okay? From 1 to 4. And let's say this here is 1, and this guy here is 8, okay? But it turns out that the average value of the function, the average value of this function, ends up being 2.5. That's the average value of the function, 2.5. Okay? Then you tell me, what must be the area under this graph from 1 to 4 if the average value of this function is 2.5 and my function goes from 1 to 4? What must be the area under that function? Who said that? Abigail, how'd you get 7.5? Yeah, beautiful. You guys okay with that? That this rectangle from here to here, where the height of the rectangle is the average value of the function, okay, the area of that rectangle is going to be equal to the area between the graph and the x-axis. That pink area is equal to this blue area. You guys okay with that? So the average value of the function times the width of the interval will always get you the area under the function. All right. Hey, there's one more thing, and that's all I got to say about that. You know, there's one more thing to show you, and I don't even have to give you any problems to do it because you can get the average value of the function, and that's all you need to be able to do. I need to show you the first fundamental theorem of calculus. And it turns out to be incredibly simple. I've only got 3 minutes, so I must show you. You know what the first fundamental theorem of calculus says?
A plus B equals C.
No. Although, you know, you're kind of close. You know, Do you know what the fundamental theorem of algebra is? Anyone ever hear of the fundamental theorem of algebra?
Oh, it's like whatever you do to one side, you have to do.
No, that's the whatever. That's one of the principles of equality. No, it says this simple. If you have a polynomial equation of degree n, then that polynomial equation of degree n has n roots. Whatever degree your polynomial equation is, it has n roots. You know, that's the fundamental theorem of algebra. Has anyone ever heard of the fundamental theorem of arithmetic? That says every number, every integer has a unique prime factorization. Like 12, you can factor it into 2 times 2 times 3. There is no other prime factorization for 12 except 2 times 2 times 3. That's the fundamental theorem of arithmetic. Well, the fundamental theorem of calculus says this. If you've got the integral of f of x dx from a to b, this is equal to big F of b minus big F of a, where the derivative of big F of x, oh, don't go, equals little f of x. Wow, I'm sorry I wasted so much time. So let me give you an example. Remember that integral we did from 0 to 2 of x squared dx, and you punched it on your calculator and got 8/3? What you're going to do on tonight's homework is you're going to take the antiderivative of x to the second power, which is 1/3 x to the third power, and you're going to evaluate it from 0 to 2. And then this is going to be 1/3 times 2 to the third power minus 1/3 times 0 to the third power, and you get your 8/3. So I'm so sorry, I was going to have you do a couple of examples, but I dilly-dallied around too much. But that's what you're going to do on problems 1 through 18 all. You're just going to be repeatedly getting antiderivatives, sticking in the upper bound, big minus sign, stick in the lower bound. Hopefully this is enough for you, so sorry. Good luck. And we'll learn where this comes from tomorrow.